Welcome students to this fourth lecture in the series on differential equations. So let's begin with where we stopped last time. Let's look at the slide. That is exercise number 10 where we stopped. We take the family of all circles touching the y-axis at the origin. And I asked you to draw these circles in blue pen and also draw with red pen circles which are orthogonal to the blue circles. And with your picture, it's interesting to compare this picture with the picture on page 635 of Resnick and Halliday's book, already cited. So the question is that, does your picture approximate this picture on Resnick and Halliday's book? The picture that you see in Resnick and Halliday's book is the picture depicting the equipotential lines and the lines of force due to an electric dipole. And the question that I have is, as the length of the dipole becomes smaller and smaller, does the picture that you have created approximate the picture on Resnick and Halliday better? Okay, I'm not sure whether I've done the sketching of those circles, but anyway, I will show you what I have with me over here. So let's see. Yeah. So there you see the blue circles touching the y-axis. I had drawn 4 of those, and I also drawn 4 red circles cutting the blue circles at right angles. And these red circles are circles tangent to the x-axis at the origin. That's a nice picture that you have, and we'll come back to this 2 families of circles in the next part of this lecture series. All right. So now let's get back to where we are. So let's go. So now let us consider another problem. Consider 2 circles with unit radii and centers 2, 0 and minus 2, 0. The circles have unit radius. The radius is 1 and the centers are placed at minus 2, 0 and 2, 0. You can easily write down the equation of these circles, right? What is the equation of one of the circles? X minus 2 squared plus y squared equals 1. For the other one, x plus 2 squared plus y squared equals 1. Now, call the first equation S1 equal to 0. The expression x minus 2 squared plus y squared minus 1, let us call it S1 for simplicity. And the other expression, x plus 2 squared plus y squared minus 1, let's call that as S2. And then let us look at this equation 1.37 in the slide. S1 plus lambda S2 equal to 0, where lambda is a real number. And as you vary lambda, you get a family of circles 1.37. So equation 1.37 represents a family of circles. And the question that has been asked is to find the first order differential equation for the family 1.37. Well, how do you do it? You take equation 1.37 and you differentiate it with respect to x. You get one more equation and you eliminate lambda between these 2 equations and you get your differential equation. Okay? Sketch the circles 1.37 with blue pen. And then, is there an exception? Is there a certain value of lambda for which this equation is not a circle? There is one value of lambda for which 1.37 is not a circle. It is some other curve, a limiting case as it were. So what is that limiting case? Point out the limiting case in your picture. Also sketch with a red pen circles that cut the blue circles orthogonally. So again, you get a beautiful picture, and In the next slide, you see those expressions Sx minus 2 squared plus y squared minus 1. When you simplify, you get x squared plus y squared minus 4x plus 3. And what about S2? X squared plus y squared plus 4x plus 3. And equation 1.37 has been written in detail in this slide. And you differentiate this equation with respect to x, you get one more equation. You get two equations involving lambda. You simply eliminate lambda and you get your differential equation for the family. Can you think of equipotential curves in electrostatics? For example, I gave you a hint. Look at the pictures on page 635 of Resnick and Halliday's book. Now you got another family of circles. Are these circles equipotential lines of a certain configuration of charges? I'd like you to think about this. Does your physical intuition help you to construct a situation? Does it help you to construct a setup, come up with a setup of charges such that the equipotential lines are exactly given by this equation x squared plus y squared minus 4x plus 3 plus lambda times x squared plus y squared plus 4x plus 3 equal to 0. Suppose you do succeed in setting up such a physical system whose equipotential curves are as in exercise 12. So, the equation depicted here are the equipotential lines. What about the lines of force? If you look at the pictures in Resnick and Halliday's book on page 635, he depicts the equipotential lines by solid lines and the lines of force by dotted lines. And what you see in those pictures on page 635, the dotted lines intersect the solid lines at right angles. The lines of force intersect the equipotential lines along right angles. So the question is that, can you figure out what would be the lines of force? The lines of force will be those red circles that you drew, and the equipotential lines will be the blue circles that you drew. Okay? Maybe as a hint, let me give you that you should think of the setup in 3 dimensions. The setup will be in 3-dimensional space, and you take in the 3-dimensional space, it will be equipotential surfaces, and you slice the surface by the xy plane and then look at the picture in the xy plane. When you take a surface and you slice it by the xy plane, you get a curve in the xy plane, don't you? So, you should do the setup in 3-dimensional space and then slice the picture by the xy plane and look at the cross section. I'll give you the answer. The answer can be found on page 107, problem 2.47 of Griffith's book, Introduction to Electrodynamics, the 3rd edition, which appeared in 1999. Please pay attention to the edition number of the book. Okay. So, this is another example from electrostatics. So, what are these examples showing you? They are showing you 2 families of curves. You got a blue circles, a family of blue circles and a family of red circles. And the red curves and the blue curves meet each other at right angles. Before progressing, let me give you 3 exercises on trying to find differential equation satisfied by a 1-parameter family of curves. Write down the equations for the 1-parameter family of circles in the first quadrant touching both coordinate axes. So, what would be the center of the circles? C, C. What would be the radius? C. X minus C the whole squared plus y minus C the whole squared equals C squared. Differentiate with respect to x, you get one more equation, eliminate C between these 2 equations and you get your differential equation. Problem number 15, you look at a parabola y squared equal to 8x and At each point on this parabola, there is a tangent line. And as the point varies along the parabola, you get a one parameter family of lines. You get the tangent lines to the parabola. So, you have got again a one parameter family of tangent lines. For example, you can take a point as at squared to at. Remember, how do you parameterize a parabola? And where the t is a parameter which varies along the real line. And for each point of the parabola, at squared comma 2at, a is 2 in this case. So, you find out the equation of the tangent at the point at squared comma 2at, and you get a one parameter family of lines parameterized by t, and find the differential equation for these lines. The third problem that I am giving you is, look at the system of curves x squared by 9 plus c plus y squared by 4 plus c equals 1. So, what is the parameter here? C. C keeps varying over the real numbers. You get a one parameter family of curves. They are conics. Some of them are ellipses and some of them are hyperbolas. Of course, if I take C to be minus 100, then there is no curve which satisfies this equation. So, C cannot be terribly negative. So, for a certain range of C from say minus 9 to infinity, minus 9 excluded, you get a family of conics. You get a one parameter family of conics, a family of ellipses and the family of hyperbolas. This family is called a confocal family. And what do? You have to find the differential equation satisfied by this family of curves. So, how do you do it? Again, differentiate the given equation with respect to x. What will you get? 2x upon 9 plus c plus 2y dash upon 4 plus c equal to 0. The 2 will cancel out. What do you get? You get the original equation and the new equation. Regard them as equations for 1 upon 9 plus c and 1 upon 4 plus c. The given equation is already on the slide. On the slide, you have the equation x squared upon 9 plus c plus y squared upon 4 plus c equals 1. After differentiating with respect to x, you get one more equation. You got two equations for 1 upon 9 plus c and 1 upon 4 plus c. Solve these two equations simultaneously. You get 1 upon 9 plus c equals whatever, 1 upon 4 plus c equals whatever. Take the reciprocals. 9 plus c equal to something, 4 plus c equal to something. Take the difference, c goes away and you get a differential equation. That will be the differential equation satisfied by this one parameter family of conics. It's a very interesting exercise. Please do it because we are going to return to this problem very soon. Okay. The next thing we do is orthogonal trajectories. If you turn to page 635 of Resnick and Halliday's book, as suggested, you would be naturally led to the following geometrical configuration of curves in the plane known as orthogonal systems of curves in the plane. So, what are orthogonal systems of curves in the plane? They are two systems of curves in the plane. A set of curves C1 and a set of curves C2. Each curve in C1 intersects each curve in C2 at right angles. Like your blue circles and your red circles. Each blue circle meets each red circle orthogonally. So, two such systems are called orthogonal trajectories of each other. So, we say that the family C2 is a system of curves orthogonal to the family of curves C1 and vice versa. The phrase orthogonal trajectories is frequently used in this context. We say that the family C2 is the orthogonal trajectory to the family C1 and vice versa, or we would say C1 and C2 are orthogonal trajectories of each other. They're orthogonal to each other. Why should we study orthogonal trajectories? Who cares about them? Reason number one, they are beautiful. Geometry is always appealing. They are pretty things. So that's good enough reason. But for those who wish to see realistic examples, they appear in fluid mechanics. They appear in optics. Recall that in optics, you got the wave fronts and you got the rays. The rays are always perpendicular to the wave fronts. So wave fronts form one family of objects and the rays form a different set of objects, and elements of one intersect the elements of the other at right angles. So orthogonal trajectories appear naturally in optics. Orthogonal trajectories appear in mathematical cartography. What is cartography? It is a science of map making. The science of map making is very old and it is very rich and very mathematical. The Finnish cartographers from Finland, they did a phenomenal amount of work. They contributed significantly to the science of cartography. If ever you have seen a globe, have you noticed that the latitudes and longitudes cut each other orthogonally? So the family of latitudes and the family of longitudes form a pair of orthogonal trajectories. So orthogonal trajectories appear in geography, and calculus plays an important role in geography. Look at chapter 8 of the book of McCleary, John McCleary, Geometry from a Differential Viewpoint is an amazing book. On chapter 8, you see cartography being discussed. There are some beautiful historical references, and he talks about some of the theorems that go back to Euler and Gauss, the two great masters of the 18th and then early 19th century. They have contributed already to cartography. Another mathematician whose name appears in the science of cartography is Lambert, who was also a mathematician. Now we shall move on to an area within mathematics and explain how orthogonal trajectories appear over here. And this area of mathematics is called the theory of functions of a complex variable. And this ideas is used by aerospace engineering. The theory of functions of a complex variables are used by aerospace engineers. So let us look at some simple examples coming from the theory of functions of a complex variables. I assure you, we will not use anything that you are not familiar with already. Nothing that I've talked here will go beyond your 12th standard syllabus. So don't be scared by the theory of functions of a complex variable. So let us take a function f from c to c given by f of z equals z squared. You separate it into the real and imaginary parts. Write f of z equals u xy plus ivxy. And so what is the real part of f of z? Write z as x plus iy and you square it. What is the real part? X squared minus y squared. What is the imaginary part? 2xy. So now let us look at the system of curves. U equals constant and V equals constant. In other words, let us look at x squared minus y squared equals A and 2xy equals B. So again, you have taken a function of a complex variable, namely f of z equal to z squared. Z is x plus iy, square it, take the real part uxy, take the imaginary part vxy. So what is uxy? X squared minus y squared. What is vxy? 2xy. right? And set u equal to constant and set v equal to a constant. So uxy equals a and vxy equals b. What is this family of curves uxy equal to a? That is, what are the curves x squared minus y squared equals a? They are a family of rectangular hyperbolas. What is this family v equal to b? That is 2xy equals b. Again, you get a family of rectangular hyperbolas. I leave it to you to verify that x squared minus y squared equals a cuts the hyperbola 2xy equal to b orthogonally. That is, if you take a point x naught y naught, which lies on both curves, calculate the slopes of the two curves at the point x naught y naught, the product of the slopes is -1. Calculus will tell you how to compute these slopes, how to compute the derivatives. To check that these two curves x squared minus y squared equal to a and 2xy equal to b are orthogonal to each other. So that gives you a very nice example of an orthogonal trajectories, two orthogonal trajectories. Here's a picture. The red curves are the curves 2xy equals b and the blue curves are x squared minus y squared equal to a. Already the picture that you see that at the point of intersection they appear to be orthogonal. The picture is fairly accurate thanks to Mathematica. And here I'd like to express my thanks to one of the students in the mathematics department, Aditya Maheshwari, who generated this picture. And the next one. Okay. Let us take another example from complex analysis. Let us take a function from which is defined on c minus 0. What is this function? F of z equal to z plus 1 upon z. This function is defined on the whole of complex plane except at 0, where it's not defined. Let us see what happens when z traces a circle r cos t plus ir sin t. So z in the domain traces a circle r cos t plus ir sin t. Remember that we are thinking of the complex numbers as points in the Argand plane. And you're familiar with this geometrical representation of complex numbers. So I can think of the complex number z as r cos t comma r sin t and let t vary. So you get a circle. The z traces a circle in the domain. What happens to f of z? What is f of r cos t plus ir sin t? What happens to the image curve? Let's see. It's an amusing exercise to understand these image curves. So what is f of z? If z is r cos t plus ir sin t, then what is f of z? R cos t plus ir sin t plus 1 upon r cos t plus ir sin t. You have to, of course, use the complex conjugate of the denominator and rewrite the thing, and you will get r plus 1 upon r cos t comma r minus 1 upon r sin t. That is displayed as 1.42 in the slide. So as t varies, what does this 1.42 represent? 1.42 is the parameterization of an ellipse. 1.42 represents an ellipse, as you very well know. A cos t comma b sin t is an ellipse. Okay, what are the major axes of the ellipse? The semi-major axis is r plus 1 upon r. What is the semi-minor axis? R minus 1 upon r. So it is an ellipse with semi-major axis r plus 1 upon r and semi-minor axis r minus 1 upon r. What is the relationship between the semi-major axis, the semi-minor axis, and the eccentricity? B squared equals A squared into 1 minus E squared. Okay, so you can compute the eccentricity of the ellipse. What are the foci of this ellipse? So what are the foci of an ellipse? It is AE comma 0 and minus AE comma 0. But what is AE? Remember, B squared equal to A squared into 1 minus E squared. So A squared E squared is A squared minus B squared. But what is A? R plus 1 upon R. What is B? R minus 1 upon R. So what is A squared minus B squared? It is 4. So A squared E squared is 4. So AE is 2. So the foci of the ellipse are 2 comma 0 and minus 2 comma 0. This is very interesting because no matter what the value of R is, you get the same foci. All these ellipses, all these image curves, as R varies, you get R cos t plus IR sin t, that you get a whole bunch of concentric circles. The image curves are all ellipses. But all these ellipses have the same foci. They are called confocal ellipses. They all have the same foci. So this function 1.41 f of z equal to z plus 1 upon z is called the Zukowski function. So the Zukowski function takes circles which center at the origin to ellipses. If you take that z traces a circle which center at the origin, the image f of z traces an ellipse. But the foci of the ellipse are plus minus 2 comma 0. So these are called the Zukowski ellipses. So the next slide is an exercise which I just done for you. Determine the foci of the Zukowski ellipses. What are they? 2 comma 0 and minus 2 comma 0. For one value of r, you don't get an ellipse. For one very special value of r. Which one? I'll leave it to you to figure it out. Next, a similar problem. Instead of taking z as a circle, as tracing a circle, let us assume that the z traces a ray from the origin to infinity. Take a ray, the ray making an angle theta with a positive x-axis. So how do you think about this ray? T cosine theta plus it sine theta, it is z equal to t into cos theta plus I sine theta. T varies from 0 to infinity and theta is fixed. So I want to find the image f of z. So f of z is z plus 1 upon z, and as t varies and theta is fixed, what do you get as the image curves? The image curves are hyperbolas. I am going to call them the Zukowski hyperbolas. Find the foci of these Zukowski hyperbolas. No prizes for guessing. They are going to be 2 comma 0 and minus 2 comma 0. The hyperbolas are also confocal and they have the same foci as the ellipses. So the entire family of conics is a confocal family of conics. Show that the Zukowski hyperbolas cut the Zukowski ellipses orthogonally. Again, we have found an orthogonal system of curves. We have found two families of curves, a family of ellipses and a family of hyperbolas. Every ellipse will cut every hyperbola orthogonally. We have a pair of orthogonal trajectories. Why is this interesting or why is this important? It's interesting because the geometry is beautiful. It's important because Zukowski employed this in the construction of airfoils. So there are applications to aerospace engineering, and I've given you a certain link for the website where you can find an article by NASA, by the Glenn Research Laboratory, where you will find details of how Joukowsky employed this in the construction of airfoils. Now, the Joukowsky function can also be applied in a very different field other than aerospace engineering, and that's what is going to be in the next slide. But before I come to that, I'm going to look at one more exercise, again from complex function theory. Here we take a different function, a very nice function. F from C to C is given by f of z equal to z squared. Show that the image of horizontal lines t plus ic. So fix your C and let t vary. So what does t plus ic trace? T plus ic is a horizontal line passing through the point 0, c. So if I take z equal to t plus ic, what is going to be z squared? It is going to be t squared minus c squared plus 2i tc. So what does this trace out when t varies from minus infinity to plus infinity? What happens? What is the curve t squared minus c squared, comma 2tc? They are parabolas. Find the focus of this parabola. And does this focus depend on c? You expect that the answer will be no, and that it will be a confocal family of parabolas, but please investigate. Now we have taken the image of horizontal lines. Let us look at the image of vertical lines. A plus it, when t runs over the real numbers, a plus it is a vertical line passing through the point a comma 0. So if I take z equal to a plus it, what is z squared? A squared minus t squared plus 2i at. So as a point in the Argand plane, we are looking at a squared minus t squared, comma 2at. This is a parametrization for a parabola. There is a parametric form for a parabola. Again, find this parabola, find the focus of this parabola, and examine whether this parabola depends upon A. The next exercise, show that the parabolas of exercise 19 cut the parabolas of exercise 20 orthogonally. Again, we see a pair of orthogonal trajectories. So now we have obtained 3 examples from complex function theory. We have not used any deep ideas from complex function theory. The theory of functions of a complex variable is a deep branch of mathematics, but we are not using any of that. We are only looking at those things that are well within your syllabus, namely how to square a complex number. Everybody knows how to do that. How to compute z plus 1 upon z. So, and just by using these elementary ideas of complex multiplication and complex division, we have obtained 3 beautiful examples of orthogonal trajectories. Okay, so now let's look at the picture. Again, Aditya has generated these pictures using Mathematica. You see, the red parabolas and the blue parabolas, you can see them intersecting orthogonally. Each blue curve intersects each red curve, and at the point of intersection, the angle of intersection is 90 degrees. So please try these out yourself. It's very amusing to do that. Now comes the promised application of Joukowsky function. The Joukowsky function in the service of astronomy, celestial mechanics. And here we come to a very beautiful theorem called Bohlin's theorem, which goes back to 1911. It is remarkable that the Joukowsky function finds applications in celestial mechanics, and those Zukowski ellipses and hyperbolas will feature in the proof of Bohlin's theorem. It's an old result due to Bohlin that the map f of w equal to w squared transforms the equations of planetary motion into this equation d2w by ds squared plus w equal to 0. This differential equation is surely familiar to you by now. Of course, the s is not the real time, it is a rescaled time. The Zukowski map and the Zukowski ellipses feature in the proof of Bohlin's theorem. Bohlin's theorem says that there is a very explicit transformation which transforms a very complicated system of differential equations, namely the differential equations that govern the motion of the planets around the sun, the two-body problem, the sun and the planet. Just these two bodies, the system of differential equation governing the motion of a planet around the sun can be transformed into this innocent looking differential equation by remarkable transformation. The motion of the planets and the evolution of this differential equation are equivalent actually goes back to Newton. But the analytical form in which we are given is due to Bohlin. You can easily use this idea to prove Kepler's first law of planetary motion. One can prove that the planets revolve around the sun in elliptical orbits with the sun at one of the foci. Reason is very simple. You can easily solve this equation d2w by ds squared plus w equal to 0. So we have to solve this differential equation d2w by ds squared plus w equal to 0. Now you see, w is a complex number. It has a real part x and it has an imaginary part y. So this equation is really two equations, d2x by ds squared plus x equal to 0, d2y by ds squared plus y equal to 0. There are two equations of simple harmonic motions. You could take x to be cos of s, y to be sine of s. More generally, you could take x to be a cosine s and y to be b sine s. And what do we get? We need to get w of s equals a cosine of s plus ib sine of s. Whereby, what is the original trajectory? Remember that the function is f of w equal to w squared. The original coordinate was z. Z was the moving point, coordinates of the moving point of the planet. So z will be w squared. So the position of the planet z of s is w of s squared, which is a squared cos squared s minus b squared sine squared s plus 2abi sin s cos s. So now if you take the real part of z and imaginary part of z and eliminate the sines and the cosines, then what do we see? We see that this is the parametric equation of an ellipse. So for example, call this real part as x of s, call the imaginary part as y of s, and so what is this equation of the ellipse? Eliminate the cosine and the sine. First write cos squared s in terms of cosine 2s, sine squared s in terms of cosine 2s, 2 sin s cos s in terms of sine 2s. Use the equation sine squared 2s plus cos squared 2s equal to 1 and you get this equation. And the equation that you see, 2x minus a squared minus b squared divided by a squared plus b squared the whole squared plus y squared by a squared b squared equal to 1. This is an ellipse foci, one of whose foci is at the origin. It's a very easy exercise in coordinate geometry and I urge you to do it. So what have we proved? We have used Bohlin's theorem to prove that if the transformed equation of W, the W equation is an ellipse, the Z equation is a square of the W equation. And the square of the ellipse is another ellipse whose focus is at the origin. So the Z, the locus of Z is an ellipse with one focus at the origin, namely the Kepler's first law has been established. Okay. Although Bohlen's theorem is a theorem on differential equations, we shall not prove it here because it is really not in the syllabus, but I just want to tell you that the theory of differential equations goes out and reaches out to various parts of physical sciences: physics, astronomy, cartography, aerospace engineering. And this theorem was already known to Newton, and it goes under the name of dual laws of attraction. I won't elaborate on what these dual laws of attractions mean. The analytical form in which we have stated the theorem is due to Bohlen. In the following two slides, I am going to give you two references, and these two references are books written by great masters. One of them was a great mathematician and the other is a great physicist. First one is V.I. Arnold. He wrote a book titled Huygens, Barrow, Newton and Hooke. And we began this series of lectures by talking about the achievement of Newton, that the work of Newton transformed astronomy from an empirical science into a dynamical science. This little book is a delightful journey through times from Isaac Barrow to modern discoveries in astronomy, spanning 2 centuries of post-Newtonian era, 2 centuries following Newton's Principia. The journey progresses with remarkable ease through the discovery of the Kirkwood gaps in the rings of Saturn, with commentaries on some of the deep propositions in Newton's Principia on algebraic geometry. Bohlen's theorem appears in the appendix, page 94. The discussion is persuasively geometric and elegant. The triumphs of celestial mechanics on page 69, the notorious three-body problem, the monumental works of Pierre-Simon Laplace, and finally Poincaré. Poincaré's revolutionary new methods in celestial mechanics are expounded by one of the most significant contributors to modern celestial mechanics. The second reference is by the Nobel laureate S. Chandrasekhar. He wrote a book, Newton's Principia for the Common Reader. It was published by Oxford University Press, 1996. This work of great scholarship is rich in content, and despite the title, it is no easy reading, but it's well worth the effort. The common reader doesn't mean the common man, it means you, the students who are concurrently learning calculus, they are learning physics, they are learning chemistry, they are equipped with enough knowledge of physics and mathematics. It is for such students that this book has been written. Of course, this book is a 600-page book and not to be read from page 1 to page 600 linearly. I recommend you directly go to page 57 and you see complete proofs of the 3 laws of planetary motion by Kepler, using the Newton's laws of motion and its universal law of gravitation. After this, you could move on to reading the supplement to chapter 6, where he discusses the dual laws of planetary attraction. And you will see a proof of Bohlen's theorem there also. And then you can move on to chapter 7 on the Kepler equation and the theorem on algebraic geometry, which is contained in Newton's Principia. I cannot resist quoting a charming essay of S. Chandrasekhar. And the essay compares the genius of Newton with that of Michelangelo. The reference is given as item number 3 in this slide. Chandrasekhar compares Newton's writings of the Principia with Michelangelo's painting of the ceiling of the Sistine Chapel in Vatican City. Chandrasekhar considers these as works of the most rarefied level of creativity. Let us see what Chandrasekhar has to say. I will just give you one excerpt from this beautiful essay, and I strongly recommend you to read this essay for its lovely style as well as the content. The Principia and the frescoes, both in their realms, are supreme, unsurpassed expressions of human creativity. I don't want to say more about these, but I hope this has enticed you into reading this essay of Chandrasekhar on Newton and Michelangelo. Now let us come to differential equations and orthogonal trajectories. Suppose we are given a one parameter family of curves C1. Is it always possible to find an orthogonal system of trajectories C2? We have seen many examples of pairs of orthogonal trajectories. But now I give you a one parameter family of curves and I ask you whether there is an orthogonal trajectory and how to find it. To understand this problem, let us assume that the system of curves C1 gives rise to a differential equation m dx plus n dy equal to 0. We have seen examples. You got a system of curves with a parameter c, you differentiate, you get one more equation, you eliminate c between the two equations and you get the differential equation. We have seen numerous examples of that kind. So now assume that this has been done and you got the differential equation m dx plus n dy equal to 0. Now, I already told you in the last lecture that this differential equation 1.43 is the differential equation for the phase curves of a first order system. What is this first order system whose phase curves are equation 1.43 or given by 1.43? dx by dt equal to n, dy by dt equals minus m. The vector nxyi minus mxyj is tangent to the curves C1. And since orthogonal trajectories are orthogonal to the original one, the tangent to the first becomes a normal to the second. So the tangent vectors to the orthogonal trajectories must be mi plus nj, because the tangents to the two systems are perpendicular to each other. The tangent to the first will be the normal to the other. So the orthogonal trajectories are phase curves of this system dx by dt equal to m and dy by dt equal to n. So the differential equation for the orthogonal trajectories is n dx minus m dy equal to 0. So given a system of curves C1, we obtain their differential equation and then we obtain their orthogonal trajectories via this differential equation. So first we are given C1. From C1 we obtain the differential equation for C1 and then we obtain the differential equation for C2, solve this differential equation and get the family C2. So that's theorem 1. Whatever I said just now can be summarized as this theorem. If a one parameter family of curves is given by the differential equation m dx plus n dy equal to 0, then the differential equation for the orthogonal trajectories is n dx minus m dy equal to 0. So under broad conditions, any one parameter family of curves admits an orthogonal trajectory. I say broad conditions because we are not really discussed existence theorems for differential equations and we are not going to. And these existence theorems will be valid under suitable conditions. But in practical situations, these conditions will always be satisfied. So now let us try out this on some specific systems of orthogonal trajectories that we have encountered. The first, of course, are the family of concentric circles. What is the differential equation for that? We have derived it. X dx plus y dy equal to 0. So what is the differential equation for the orthogonal trajectories? Y dx minus x dy equal to 0. It's a variable separable equation and the solutions are y equal to mx or x equal to my. So the orthogonal trajectories are lines through the origin, and everybody knows that a circle with center at the origin cuts a line through the origin orthogonally. Let us take the next one. Let us take the hyperbolas x squared minus y squared equal to c. Differentiate, the c straight away disappears. You get x dx minus y dy equal to 0. What are the differential equations for the orthogonal trajectories? Y dx plus x dy equal to 0. Solve this differential equation, which is a variable separable equation, and you get mod xy equal to c. Remove the absolute values and you get rectangular hyperbolas cutting the members x squared minus y squared equal to c orthogonally. Now let us take another example. You take this one parameter family of curves y equal to c e to the power minus x squared. Find the orthogonal trajectories. You differentiate it, dy by dx equal to, straight away you get minus 2xc e to the power minus x squared, but c e to the power minus x squared is y. So you get dy by dx equal to minus 2xy. So the differential equation for the family of curves 1.47 is what? Dy plus 2xy dx equal to 0. The differential equation for the orthogonal trajectories is 2xy dy minus dx equal to 0. We shall regard x as a function of y and integrate. The solutions are mod x equal to a e to the power y squared, where a is a positive constant. Remove the absolute value and you get a family of orthogonal trajectories. Note that x equal to 0 is not included in here because we are dividing by x when you do the method of separation of variables, and x equal to 0 is also a special solution, and we get, that is understandable because all the curves of the original system are bell-shaped curves. They all have horizontal tangents when they cut the y-axis. And so the removal of the absolute value term will give you x equal to c e to the power y squared, where c is any constant. Well, now we come to a couple of examples. So determine the orthogonal trajectories for the family of parabolas y equal to kx squared. That's the first problem. The second problem is consider the family of circles touching the y-axis at the origin. Find the differential equation for the orthogonal trajectories. Mind you, I am only asking you to find the differential equations for the orthogonal trajectories. Integrating the differential equations will be done in the next chapter when we discuss homogeneous differential equations. And then consider the function f of z equal to 1 upon z. Find the images of horizontal and vertical lines under this map f of z equal to 1 upon z. Obtain the family of curves and relate it to exercise 23. We have done a similar exercise with parabolas. Now I am asking you to do the same exercise with f of z equal to 1 upon z. You will get a fourth example coming from complex analysis. And the last slide is two more exercises for today's lecture. Find the differential equation for the orthogonal trajectories for the one parameter family of coaxial circles 1.37. Remember that S1 plus lambda S2 equal to 0, where the circles had centers 2, 0 and minus 2, 0 and radius 1. And we got a family of coaxial circles. Find the differential equation for the orthogonal trajectory. I'm not asking you to solve the differential equation, just obtain the differential equation. And finally, the family of confocal conics. I asked you to determine the differential equation for this family of confocal conics and find out the differential equation for the orthogonal trajectories, you will see something amazing happens, and I'd like you to find an explanation for this phenomenon. I think we'll stop here for today and we'll continue this series of lectures. And in the next lecture, I will discuss homogeneous differential equations. Thank you.